Hi, my name is Łukasz and this tutorial is created for my blog Enterfea.com. Today I want to show you how to implement materially nonlinear analysis in shell design. Firstly, we will create a shell model with geometry and parameters identical to the ones used in models in previous examples. So let's create 2 points. I will then connect those points into a line and rotate this line to create a shell. And Femap has a nice revolve command to do so. I have to define the vector of rotation. I will use a vertical upward axis, and half of the width of the support will be 5 degrees as previously. As you can see, part of the shell is already made, and to make things easier, next I will highlight the line, the vertical line, to rotate again with a box. And this is the half of the model. Actually, we could use it as a final model with symmetry boundary conditions in the middle of the support, but I don't like to have symmetry boundary conditions where the problem really will be solved, where the critical area is. So I will create the second half of the model. For that, again, I will pick a line, and now I will rotate in a reverse direction, so I will locate the vector downwards, because Femap do not like negative values of angle. And last time, and 40 degrees. This way we have created a shell geometry. This is 25% of the shell, because this is a whole shell supported on 4 supports, but since the model is symmetric, we are using only the 1/4 of the model. So now I will go into model, in model info tree, and this tree actually guides us neatly through everything we have to define. So firstly, we'll define the material. Usually I define steel with 205 gigapascals of Young modulus. I'm aware that Eurocode actually suggests value 210, but I'm simply used to this value. Also, for now, I will not define any nonlinear parameters. We will get here later on, and it's done. And we have to create a property. A property is the place where we explain that we want to use a material, and since we are using shell elements, we have to define thickness. In this case, since everything is in meters, that 1 millimeter is exactly this much, so we have a property. Of course, Femap does not know that we want this property to assign to each shell, so we have to do it manually. We can select all shells and simply pick the property we have defined. Also note that I will use quad elements without mid-side nodes. And since we are defining mesh parameters, I will also use default size, and I will pick 10 millimeters as a default length of edge of one finite element. If you are interested in how to pick which element size is correct, I have a separate post in my blog about this. So, shell parameters are done. Now let's go to the loads. So, load case 1. Okay. We wish to have a vertical downward load on the top of the shell. We'll use force per length. and in previous examples it was 50 kilonewtons per meter. I will use cylindrical coordinate system. I will explain later why, because obviously in rectangular this would work perfectly fine as well. Vertical axis is upward, so I need a negative value, and it's done. So now let's go into constraints, so boundary conditions. First, I want to create a symmetry boundary condition, and this is a place where the cylindrical coordinate system comes in handy, because I don't have to worry in which axis this direction is that I need to restrain the symmetry boundary condition. I can simply say this is on the angular part of cylindrical coordinates, and this way I don't have to define any local coordinate systems to do so. So it's nice, and also some solvers do not like when you mismatch coordinate systems between loads and boundary conditions. This is why I used cylindrical coordinate system everywhere, even though rectangular would be just as good. And it's done. I want to have a support that prohibits radial movement on top and on bottom, but I only marked top lines. I will mark bottom ones later on to create a secondary set, because I like to have things separated. I can name this top, and then after a while, when I get back to this model, or I simply wish to see what is happening, I have a clear division between what is constrained where. It is easier to follow. Okay, so now let's go on the bottom. Note that I am not picking those two lines. This will be a support, and I don't wish to have two sets of boundary conditions in one place. Again, bottom, same thing, and finally a support. Last thing to do before meshing is to check whether or not surface normals are in the same direction. As you can see here, I've pressed F6, and here we have curve surface directions, show surface arrows, and you can see that the normal of the shells are in two different directions. Actually, this may cause some problems, so I wish to change it. I will go to modify, update other, and surface normal. This one and this one in the other direction. I will rebuild the model to update it, and again F6, show arrows, apply, and now we can see that all normals are in the same direction, in the outward direction. It actually doesn't matter whether this is an inward or outward direction, as long as it's constant on all shells. So we're happy with the result, and we can mesh our model. And it's done. At this stage I usually hide most components of the model to clearly see the finite element mesh. And since this is complete, actually before running a nonlinear analysis, I will make a linear one. Oh, I have one already defined, but let's do it again just in case. So I will delete this one and create it again, so you see how to make new one. Static linear analysis. This is such a simple design that I won't even go into details. I don't want to set anything. I simply press OK and analyze. It will take only a second to calculate, and it's done already. You can see here the outcome. This is how it looks like. So the formations look smooth. We can easily see that there is a point or small support here. Also, symmetry boundary conditions seems to work. So I would say that the model is okay. Everything went fine. Since that's the case, we can now create the nonlinear analysis. Firstly, we wish to make our material nonlinear, and the easiest way is to introduce plastic nonlinearity. That would be 235 and 60, so megapascals, and I use von Mises yield criterion, of course. Now, linear analysis we have defined previously will show exactly the same outcome, because linear analysis, as the name suggests, cannot take into account material nonlinearity, so we have to define a nonlinear analysis. That would be material nonlinear analysis, and the solution we will be using is 106, solution 106. It actually makes sense to pick more processors for that, because it will last a while to calculate this. And also note that Femap by default already says that we are using large displacement. This would be a geometric nonlinearity. I don't want to have that in that model. For now, I wish only to have a material nonlinearity with linear geometry, so I had to switch this off. And now we go through the dialog to nonlinear control options. Increments or time steps. This is the value called nint in Femap, in Nastran dictionary, and what it does is I applied 50 kilonewtons per meter or on top circumference, and this is the amount by which it will be divided to create the first increment, load increment, which means that in this case I have 50 kilonewtons per meter divided by 50, so the first step, the first increment of load will be 1 kilonewton per meter on top, and I'm fine with the value. Also, I wish to have maximum of 5 iterations per step, per increment, which means that if the new increment is implemented and in 5 tries the convergence is not met, the analysis will fail. And also, there is a way to implement negative value of certain of those parameters, which has an influence on general solution method, but I don't want to go into those details today. Also, we want to have intermediate results, of course, because this will allow us to see all the steps, and we will be using arc length method. I described this on my blog in previous posts. We will use modified Rix, and we won't speed up nor slow down the arc length. Of course, I desire to receive a solution by only one iteration. It actually changes a bit how the solver approaches the problem. So basically you could either say, well, I want to have less increments but more iterations, or vice versa, I will use more increments but less iterations. And I think that less iterations is better this way, that you can see the steps of the analysis more. The cinematic also looks nicer. And I want to have maximum amount of increments by 150, which means that theoretically, if everything will go linear, I will obtain the load which is 3 times as high as the one I've implemented in the model, because I divided it by 50, but in 150 steps I will be 3 times more away with the load. Of course, this won't happen. The capacity of the model is much smaller, which means that most of the increments I've chosen here will be in post-failure part of the model analysis, which means that we will see what is happening after the model lost capacity. And this is of course useful because we can trace and see how the failure actually happens. So let's go next. We'll use boundary conditions and loads we defined previously. Rest is okay for here. And Femap suggests what the outcome should be, and I'm fine with that. So everything is fine. We can press done and analyze the problem. This one will take a considerable amount of time, And when doing such analysis, I like to go to nonlinear history, and you can see a chart here, and also a current iteration. Unfortunately, this is not an increment, it is only an iteration, which means that you cannot be certain how many times the load was increased so far, because as you remember, I said that each increment can have up to 5 iterations, so we cannot be sure whether this means that 24 we have now means that there were only 5 increments and each required 5 iterations, or there were 24 increments and each only had 1 iteration. So it's kind of hard to know exactly where you are in the analysis, but looking at load factor, you can see that firstly, iterations were going smoothly and the load increased nicely. The 0.4 here, or 0.5, means that by this amount the applied load was multiplied. So this would be 0.5 multiplied by 25 kilonewton per meter of circumference. And also, you cannot think about it as a stability plot, because here this is not a deformation, this is only iterations. So if more iterations are needed to obtain a convergence, we can assume that this has to do something with plasticity, because it is harder to reach convergence then, and perhaps more iterations will be needed. So the more iterations you need in one place, the longer the horizontal line gets, which means the bigger problems the solver has to find the answer. But of course, this is not a stability plot, it only shows you with certain amount of expertise, you can kind of see where you are in analysis, but that's basically it. So I will pause recording for a second, so you can see that up to this time it's 2 minutes and a half, and I will pause it so you don't have to wait and watch for a few minutes. It is also perhaps important to note that in my estimations, usually in shell design I require somewhere around 3 iterations per increment on average. Well, to be honest, I never actually made the statistics for it, but I think that it would be something like that. So this means that we will be waiting for something like 400-500 iterations in this problem. But of course this depends greatly on many things, and those are the things like how big the plasticity zone will be, how much yield will there be in the model, if the geometry nonlinearity is present or not, and many different things as well. So of course this is not something to be treated as a constant. As you can see, 9.5 minutes have passed and a fatal error appears. This fatal error, if we look into details, is NL iter, which means that the maximum number of controlled increments has been exceeded. And since we defined 150 iterations, we can be sure that this is the amount that we have made. And also, if you can see that the load factor was really close to 1, if we were to reach 1, then this would mean that the analysis would simply stop, because we have reached the load we applied. So by pressing OK, we have to wait a bit for Femap to actually read the results from Nastran analysis, and it's done. You can see now that firstly the process is linear, and then here first plastification, yielding is occurring here, and of course as we move on the zones are getting bigger and bigger. you can see, well, the deformations are actually exaggerated, but you can see that the shell is actually being going through the column. If we scale the deformation to the actual size, this is only a small displacement, but at this stage we can be certain that the model is destroyed, because it simply starts to punch through the support it's standing on. Of course, we can animate this to see how it looks like. You can see how the yield zone develops, and that's basically it. As I wrote in my post, actually it's quite hard to tell at which stage the model is destroyed. Well, we can be fairly certain it is not where the first yield appears, but it must appear somewhere in that scope. So let's create a stability path, which is a tool useful in problems like that. So we will go into charting and create new data series that is against set value. Set value is a multiplier, a load multiplier that was used in the iteration that we are looking at right now, which means that this is actually a load value, if somehow not easy to see, and by displacement we will use a vertical deformation of this node. And when I press OK, you can see the stability path. Well, this one point is because I used all output sets, and actually what I should have done is to start from case 1 and go to the last one, because pressing all meant that also the linear analysis was taken into account, and of course it had certain displacements, so it does not fit, especially since it doesn't have the set value, which means 0 in Femap terminology. Well, you can see that this is a stability plot, but rotated 90 degrees, and this is a displacement, and this is the load multiplier, which means this is 50 kilonewtons per meter multiplied with 0.5 here, for instance, or 0.8 here. So first thing you can see is actually that it always rises, that it does not collapse. In collapse we would assume that it should go up and then downwards, because the load is decreasing because the model is collapsing, as it is in geometrical nonlinearity. But with material nonlinearity the problem is a bit more complex, and even though we may be quite certain that at this stage the yield zone is so big and deformed that it actually means that the model is destroyed, and this is hard to read from stability plot, and there is a way to do it. It is called modified southward plot. It is a method to obtain outcome from such stability path, but this is a topic for the next post. For now, we have created a material nonlinear analysis and obtained the stability path for the analysis. If you wish to use this chart in Excel sheet, you can go here and copy chart values and simply paste them into your spreadsheet in Excel and create a chart of your own. It will simply work. Just remember that this is not the load, it is only a multiplier of the load applied, so in this case multiplier of 50 kilonewtons per meter. So this is all for today. Thank you for watching, and I hope you find this tutorial useful. If you have any comments, you can leave them on my blog or under this video. Have a nice day. Bye.